Yes. So next most intermediate is free radical. So free radicals are trivalent carbon intermediates having one non-bonding electron. So one non-bonding electron nothing but one electron which is not involving in bonding. So next is, it is an odd electron species. Due to this particular property, it is found to be odd electron species. Okay. Now it is unstable, reactive. So due to one non-bonding electron, it is found to be unstable and it is reactive, and finally we can say paramagnetic as well as septate electronic species. So it is electron deficient. Why it is electron deficient? Due to presence of only 7 electrons. Okay. And finally we can define like this: free radicals are a formally neutral charged species. So we can't write any charge here, formally neutral charge. Free radicals are formally neutral charge. We can't write any charge on free radical, especially carbon free radical. Okay. Next, if I take a carbon, now I am writing 3 bonds: hydrogen, hydrogen, hydrogen. So here one free radical I am writing. This is non-bonding electron. So this is called a non-bonding electron. Now how many bonds are present here on carbon? 3 bonds are present. So what is the hybridization of free radical? sp2. Now it is found to be trigonal planar geometry. Trigonal planar geometry. What about bond angle? Bond angle is 120. It is approximately similar to carbocation only. Okay, sp2 trigonal planar, 120 will be the bond angle. And even under conjugation, see, if free radical even under conjugation whose hybridization is remain same. Now hybridization is sp2, now followed by trigonal planar geometry. Simple molecules as well as free radicals which consisting one electron, even it is under conjugation, that becomes a trigonal planar sp2 hybrids. But in case of carbanion, simple is sp3, conjugate is sp2. That is the difference. So we can also define like this: a molecules which carry an independent electron which is not involving in bonding, that is called free radical. So free radicals may carry one electron, or free radicals may carry more than one electron. Suppose if molecule carry, suppose A is a molecule which carry only one radical, this is called a single electron radical. This is called single electron radical. Single electron radical. We can also say radical. Okay. Suppose some molecules I am saying they carry 2 independent electron. It is not a lone pair. First remember, it is not a lone pair. 2 independent radicals are there. So that radical is nothing but a biradical. Free radicals are monoradicals. At the same way they may also show a biradical system. So biradicals nothing but 2 independent electrons which are not involving in bonding. So structure is most important. Structure is trigonal planar. Hybridization is sp2, bond angle is 120. Is it paramagnetic or diamagnetic? Paramagnetic. This point is very, very important. Paramagnetic, formally neutral charge. So in case of carbanion, we are writing negative charge. But in case of free radical, don't write negative charge. Simply leave it. We can't write CS3 minus here. So it is only CS3 dot. CS3 dot means we can write like this. CS3 dot, which means it is an electron belongs to carbon. This is actually carbon electron. It is also carbon electron. It is carbon. It is also carbon electron. Out of 4 electrons of carbon, 3 electrons are involving in bonding. 1 electron is not participating in bonding. That's why it is called free radical. Clear? Next, generations. How to generate a free radical? Generations of free radical. So first method is thermolysis. By heating, suitable bonds have a tendency to generate a free radical. Free radicals can be generated by heating under suitable thermal conditions. Best example, see, I am using a tetramethyl lead. When tetramethyl lead on heating with a suitable temperature, So 4 equivalents of methyl radicals are going to be generated and followed by loss of lead. And one more, we can also use tetraethyl lead. This is called TE, tetraethyl lead, TEL, anti-knocking agent. TEL is anti-knocking agent. How many ethyl radicals you will get? 4 ethyl radicals and then followed by lead. What is this? This is very important one. TEL, tetraethyl lead, anti-knocking agent. Which among the following is anti-knocking agent, I will ask? Tetraethyl lead is a anti-knocking agent. So tetraethyl lead on heating, that will give 4 ethyl radicals and then lead. Okay. Next, not on this, we can also use a benzoyl peroxide. See, this is called benzoyl peroxide. This is on thermal heating. Can I break this? Benzoyl peroxides are highly sensitive with thermal conditions. How many benzoyl radicals we are going to extract? Benzoyl peroxide radical like this. Okay. You know, this is called azomethane. Nitrogen, nitrogen, triple bond, and see, this is triple bond becomes double. Now, this is under thermal. This is called azomethane. Azomethane on thermal, decomposition of methane, 2 equivalents, and then loss of N2. So break these two. This and this removed in terms of radical, and there is loss of N2. Azomethane. What is that molecule name? Azomethane. Next, this is azobutane. Azobutane on thermal decomposition. Can I break this? Now, how many radicals you will get? 2 radicals and then followed by N2. This is called this is azobutane, azo tertiary butane. Clearly, if you want to write, azo tertiary butyl butane. And this is one more. This is well known for you. Nitrogen, nitrogen double bond, and this carbon, nitrogen triple bond, carbon, nitrogen triple bond. So this is called AIBN, azobis, isobutyronitrate. Azobis, isobutyronitrate. This is AIBN used in TBTH. In tin OMC, it is most common radical initiator. So thermally, what you will expect? Break this bond, break this bond. Now here, you may get a radical, and then what is removed here? N2 is removed. Azomethane, azo tertiary butane, names are very important. Azo tertiary butane, azobis, after writing bis, enclose in box, isobutyronitrate. It is very important. Regularly it will come for initiating any radical. Radicals are initiated by this kind of radical initiators. Azobis, isobutyronitrate. So in many named reactions and many rearrangement reactions, radical initiations are very important. So you try to listen reactions and their mechanisms clearly. Clear? Next, we can also initiate by photolysis. So this is nearly 300 degrees, 100 degrees centigrade of temperature is required, and this is normal warming is sufficient. Last case, azomethane required 100 degrees, 300 degrees centigrade of temperature. Last case, high temperature required for azomethane. Why? Because you are getting a stable radical, required less energy. Last case, azomethane required 300 degrees centigrade of temperature, but right now 100 and normal heating conditions is sufficient. What is photolysis? Photolysis is nothing but irradiating any organic molecule with a suitable photons or suitable wavelength of UV. Okay. Now photolysis reactions are approximately similar to thermal reactions. Sources for generating radicals are same, only symbol is different. Now we are not heating, we are irradiating. Now simply can I break here? Break this. After breaking, what do you expect? pH, C double bond O radical. How many equivalents? 2 equivalents. Benzoyl peroxide. This is benzoyl peroxide. Can I take hydrogen peroxide? Hydrogen peroxide on photolysis, what do you expect? Hydroxy radical. And if I take dialkyl peroxide on photolysis, what do you expect? Alkoxy radical. How many equivalents? 2 equivalents. Okay. Now even we can also take a azomethane. Nitrogen nitrogen double bond with CH3. This is called azomethane. Azomethane on photolysis. Azomethane on photolysis. Can I break this? Break this. What do you expect? How many methyl radicals? 3 methyl radicals and then loss of N2. Okay. Next, even we can take acetone. Acetone also undergo photolysis photochemically. Now break this bond. After getting this, you may get a acyl radical and what is one more? Methyl radical. So most commonly here we can also expect 270 nanometers of wavelength, which is suitable for irradiating carbon-carbon bond. It will come one more time in photochemistry. I will explain completely in photochemistry. So what is a suitable wavelength to irradiate a organic functional group to get a radical? So what is our final target? Our final target is to generate a free radical by using thermal conditions as well as photochemical. So what are the sources available to generate a radical? The common source is peroxide, acyl peroxide, alkyl hydrogen peroxide, okay, then followed by diazomethane, azomethane, diazo as well as azomethane, okay, but they will give a biradical, that is the difference. Diazo will give biradical, azo will give monoradical, okay, then followed by some selective azo derivatives, A, B, N, etc. This concept is not only helpful for this chapter, it can also help in other key chapters, especially reagents, oxidations, OMCs, at the same way photochemistry. So everywhere this chapter will give you more information to initiate a organic reaction. So that's why you should be very strong in reactive intermediates, how to initiate, how to participate, and what kind of chemical reactions are expected. Now, so you know very well, when two halogens are get combined together, that can be photochemically irradiated and we can generate a biradical having two different halogens, right? Chlorine under photolysis will give chlorine radical or not? This is well known. Where you observe this one? From your intermediate onwards you are learning this one. Free radical substitution. Alkanes undergo which reaction? Free radical substitution. So that is the specialty of this concept. Means approximately every chapter either cation, anion, radical, carbene, nitrene or benzene are the key participators in a chemical reaction. So that's why you should know where that particular intermediates are involving. You know chlorine undergo free radical substitution. This I will show one more. Chemical reactions, this reaction will come one more time. You can take all kinds of halogens starting from fluorine, chlorine, bromine, iodine, but preferred is iodine. Okay, iodine, bromine, then followed by chlorine and fluorine, that will generate a radical. What is this? Chlorine radical, Cl dot, Cl dot. Now, even I can take hydrogen on photolysis. Can I get radical? Now, I am taking hydrochloric acid, HCl, HX, HBr even. You know Markovnikov rule, anti-Markovnikov rule. Even HBr also undergo photolysis, that will give hydrogen radical, bromine radical. This will follow anti-Markovnikov addition. HBr. Now, we can also take ROCl on photolysis. You may get alkoxy radical followed by chlorine radical. Hypochlorite, this is called hypochlorite. Now, RONO. Now simply break this photolysis, that will give RONO. Hyponitrite. This is alkyl hyponitrite. This is called alkyl hyponitrite. This is chloride, now this is nitrite. Hypochlorous acid, you know HOCl. HOCl nothing but hypochlorous acid whose corresponding derivatives are hyponitrates, hypochlorites. Clear? You should remember this: free radical substitution reaction, normal hydrogenation reaction, anti-Markovnikov rule. Okay, now hypohalide additions, Barton reactions. So that is the specialty of this one. If you know these concepts clearly, name reactions will be in your hand, rearrangements will be in your hand, and every chapter, even if you don't know the chapter chemical reactions, if you know reactive intermediates clearly, you can guess the answer. That is the specialty of reactive intermediates. You need to focus each and every reaction involved in reactive intermediate. Can I close this? Right. Now, what is a redox reaction? Oxidation and reduction, commonly known as redox reaction. So, free radicals also involve in redox reaction. So, loss of electron is called oxidation, gain of electron is called reduction. Okay. Now, see, I am using a peroxide, acyl peroxide. This is called acyl peroxide. Acyl peroxide on treatment with copper 1. Now, what happens? See, this will break this bond. Here one radical is present, already one more radical. Copper plus 1 will donate one of the electron. That electron will be added either this oxygen or this oxygen after breaking. When copper plus 1 donates one electron, copper becomes, how copper becomes? See, this is C double bond O, here this is O radical. When you break this bond, here already one electron is present on oxygen, here one more electron present on oxygen. Any one of this oxygen radical will take one of the electron from copper. So, can I write, suppose if this particular part will take electron, what should I write? Can I write 2 electrons here? This electron is already belongs to oxygen and one extra electron I am writing which is coming from copper. Can I write -1? This is -1. So, what is -1 indicates? One extra electron. Okay, -1 indicates always one extra electron. Now, what about copper? Copper plus 1 becomes +2. Now, copper plus 1 converted to +2 means, is it oxidation or reduction? Loss of electron, right? +1 converted to +2 means, here it is loss of electron. Loss of electron is nothing but oxidation. Now, this molecule, especially this part I am saying, this part is gaining electron or not? Here this oxygen having one electron, now it is gaining one extra electron from copper. So, can I say gain of electron? So, gain of electron is nothing but reduction. So, simultaneously this reaction is called redox reaction. This you remember. Loss of electron by reagent, gain of electron by substrate. So, now this is called a redox reaction. Reduction as well as oxidation. Clear? Try to understand the logic involved in any concept. Every time what is our target? Our target is to generate free radical. So, we are generating free radical and what kind of reaction we are implementing for generating any radical. That point you remember. Okay. Now, see, this is well known nitrogen nitrogen triple bond, and this is plus and this is Cl. Aryl diazonium chloride. What is this? Aryl diazonium chloride. When aryl diazonium chloride reacts with copper 1, cuprous, copper 1 is nothing but cuprous. Okay. Now, when you break this bond, and if you break the bond present between benzene and nitrogen, if I break this, then what happens? Benzene carry one radical or not? And what about nitrogen? Nitrogen carry one radical. See, already this nitrogen having lone pair. Here they carry already lone pair. On this nitrogen, how many lone pairs are there right now? In this case, this nitrogen carry no lone pair. They carry only one electron. When copper give one electron to this nitrogen, this electron and copper electron both are belongs to a lone pair or not? It is a lone pair. Can I write like this? Now this is this electron, and what about this electron? This electron coming from copper. Okay, and what about chlorine? Chlorine is removed in terms of Cl minus, and copper is converted to copper plus 2, right? Copper plus 1 converted to plus 2. Now copper loses one electron or gains one electron? Loses one electron. So this undergo oxidation. And what about in this case here? Nitrogen carry only one electron. Now nitrogen carry its own electron only, but it is loosed. That loosed electron, it is taken from copper. So it is get balanced. So that's why don't write negative charge here. Already this nitrogen loses one electron, and it was covered that electron by taking from copper. So that's why here don't write negative charge here. But copper is giving one electron to nitrogen, and finally copper becomes copper plus 2. Now what about benzene? Benzene carry one radical or not? And what about chlorine? Chlorine minus 1 means chlorine carry how many extra electrons? Chlorine carry how many extra electrons? One electron. Suppose when chlorine carry one extra electron, that extra electron is given to copper plus 2, this one. Now copper plus 2 will take electron from here. Now it forms chlorine radical, and what about copper? Plus 2 becomes plus 1. Is it right? Why? Because copper is giving to system, then it will take electron one more time from the system. Then copper plus 2 becomes copper plus 1. Now what about this? Chloride ion becomes a chlorine radical. Now what are leftover radicals? Aryl radical, and what is one more radical? Chlorine radical. These two get combined together and finally forms aryl chloride. What is this reaction? Sandmeyer reaction. This is called Sandmeyer reaction. Conversion of aryl diazonium chloride to chlorobenzene. You know this one. Sandmeyer reaction is this one. I am using a aryl diazonium chloride to what I am converting? I am converting into chlorobenzene. So what is the reagent used in this one? Copper plus 1, CuCl or Cu2Cl2, like that. Anything they will give. CuCl, Cu2Cl2. Getterman reaction also possible, but that is different little bit. So pure metals we are going to use. So Sandmeyer reaction is nothing but, what is Sandmeyer reaction? Conversion of aryl diazonium chloride to chlorobenzene. Now this is proceeds with a two mechanisms. One is radical mechanism, one more is ionic mechanism. Right now our concept is radical mechanism. I given this reaction with a radical mechanism. See, I taken aryl diazonium chloride. Finally what I prepared? Aryl chloride. Aryl diazonium chloride, I prepared aryl chloride. Otherwise you can say chlorobenzene. Both are same. Some name reactions also going to come. Okay, so first reaction regarding radical is Sandmeyer. Conversion of aryl diazonium chloride to chlorobenzene, otherwise you can use bromobenzene even. But we can't prepare fluorobenzene and iodobenzene by using this method. This I will explain in reaction mechanism, there it will come one more time, and individual chapters also it will come. But right now you remember what is a Sandmeyer reaction. Aryl diazonium chloride to chlorobenzene in presence of a copper 1 salt. That copper 1 salt is nothing but cuprous chloride or cuprous bromide. If I use bromine, you will get bromobenzene, that's it. That is redox reaction. Next is, I am using iron plus 2 in presence of hydrogen peroxide. What is this reagent? Fenton's reagent. This reagent name also they are asking in exam. Fenton's reagent. Ferrous sulfate in hydrogen peroxide. Ferrous in hydrogen peroxide is nothing but Fenton's reagent. Fenton's reagent. Okay. So remember, Fenton's reagent is used for hydroxylation reactions. Means introducing hydroxy group on aromatic systems, this reagent is going to be used. Hydroxy group on aromatic systems. That's what is called hydroxylating agent. Which among the following is hydroxylating agent? Best example is Fenton's reagent. What is this? Ferrous, not ferric. This reagent combination also they will give in your exam. Ferrous sulfate in peroxide. Okay. Now see, generally if I take a hydrogen peroxide, it is a open book structure. Now if I use a ferrous, what is it? Charge present in ferrous plus 2. Now when ferrous breaks bond present between two oxygens, now here you will get one radical, oxygen one electron, here oxygen carry one electron. Now iron will donate one electron here. When ferrous donate one electron, what happens? This becomes a hydroxy radical, and what about one more? Hydroxy anion. Can I write anion or radical? Anion. And what about iron? Iron becomes plus 3. Ferric becomes, ferrous becomes ferric. Is it losing electron or gaining electron? Losing electron. So from here to here it is oxidation, and this is undergoing reduction. Loss of electron, gain of electron. Two things are happening here at a time. Okay. Now after that, the hydroxy radical which is formed is going to react with a benzene. This is hydroxy radical. It is going to break this bond. Now here I am writing one radical, here one radical. This radical get combined together. So after combination, can I write hydroxy here? Now this radical combined with this one by leaving this radical. Can I write? Now after writing this, here one hydrogen atom is present, break this bond. This radical get combined and forms a double bond or not. And what is the final answer? Phenol. We can convert benzene to phenol by using Fenton's reagent. So after getting, how this hydrogen is removed here? Hydrogen in terms of radical. Now the removed radical is going to deliver one electron to ferric. Now this electron is donated here. Then what happens? If ferric becomes ferrous, hydrogen becomes H plus. Now this H plus is combined with the negative ion which is formed initially. Okay, this is OH minus. Now this OH minus and H plus get combined and forms water molecule. Now what is overall reaction? Overall reaction is we are taking benzene molecule and I am using iron plus 2 in hydrogen peroxide. So what you are preparing now? So we are preparing a phenol. So this is preparation of phenol. Fenton's reagent is a hydroxylating agent. What we are adding now? Hydroxy group on benzene. Here there is no hydroxy group. Right now we are introducing hydroxy group on benzene. So remember, when Fenton's reagent is given, it is used to make insertion of hydroxy group on aromatic systems. So it is nothing but a hydroxylating agent. This is overall Fenton's reagent reaction. Next, one more, auto-oxidation. Auto-oxidation is one more method to generate a free radical. Self-oxidation nothing but auto-oxidation. Own molecule is a oxidizing agent for own molecule. Two molecules will be there. First one molecule responsible to undergo oxidizing agent, and that will oxidize second molecule. So that is called auto-oxidation, also called self-oxidation. See, here I am using a benzene attaches to C double bond to H, benzaldehyde. When benzaldehyde on treatment with iron plus 3. Now can I break here? I am breaking one bond. What happens? See, this electron is added to iron. So when one of the electron added to iron plus 3, now hydrogen becomes H plus, iron becomes plus 2, right? Now hydrogen giving electron. Reagent is taking electron from substrate. Okay? So after this, one more choice is there. Now if this reagent want to reorganize its original structure, they should donate one electron here. So finally what happens? Iron plus 3 and there is a formation of hydrogen radical. First, whenever if I use ferric, that will break this bond and take one electron from hydrogen. After taking electron from hydrogen, hydrogen becomes H plus, ferric becomes ferrous. After breaking one more time, it will deliver one electron that is taken by hydrogen and you will get this one. And finally what happens? See, this is called benzoyl radical. When benzoyl radical on treatment with oxygen, O2, okay, atmospheric oxygen, now break this bond, this radical combine with this radical. After breaking this one, what will you expect? C double bond O. Now what about this? It is connected to one more radical or not? Can I write like this? Break this bond, here how many radicals you will get? 2. Now this radical combine with this one and forms a bond, and this radical is left on oxygen. Now this radical combine with this radical, hydrogen radical. So after combining, what will you expect? PH C double bond OOH. Now see, this is called benzyl peroxide, okay, otherwise perbenzoic acid. What is this? Perbenzoic acid, otherwise benzoyl peroxide. Now I am reacting with the same molecule, C double bond to H. What is this? Benzaldehyde. What is this? Benzaldehyde. Benzaldehyde itself, it is undergo a oxidizing agent for benzaldehyde. Benzaldehyde first converted to perbenzoic acid. That perbenzoic acid makes oxidation on this one. So this will deliver one oxygen here, and finally see this molecule is get converted to benzoic acid. Now this is oxidizing own molecule. This molecule is coming from which reagent? This is coming from benzaldehyde. This is coming from benzaldehyde, and this is oxidizing own molecule. That's why it is called auto-oxidation. I am using two benzaldehydes. This is first benzaldehyde. First benzaldehyde get converted to perbenzoic acid. After converting into perbenzoic acid, this first molecule oxidizing second molecule, and both are get converted to, how it is converting? Benzoic acid. Both are oxidized or not? Both are oxidized. First one is reacted by a metal, and it will spontaneously reacts with atmospheric oxygen and converts into perbenzoic acid. And first molecule is oxidizing second molecule. So is this oxidation taking place on own molecule or not? It is not oxidizing a new molecule, it is oxidizing its own molecule. That's why it is called auto-oxidation. Now it is proceeds with a which mechanism? Radical mechanism. Next, anodic oxidation. What is anode? Which terminal? Positive or negative? Anode. Anode means positive. Anion means negative. Anode means positive, cathode means negative. Anion means carbanion, negative. Carbocation, positive. Okay? Cation, positive, cathode, negative. So, anions migrate to anode, cations migrate to cathode. Okay? So, anode is nothing but a which terminal? Positive terminal. Okay? To this positive terminal, which ions are going to come? Anions. Suppose if I take a carboxylate ion, this is carboxylate ion. Now, carboxylate ion is closer to anode. Okay? So, after coming closer to anode, they may lose electron. Now, this anion is losing electrons to terminal. What is this terminal? Positive terminal. Now, they are losing electrons at which place? Now, see, this anion is approaching around positive terminal. At positive terminal, they are losing electron. If this anion loses electron at positive terminal, what is that reaction? Oxidation or reduction? Loss of electron. Loss of electron is oxidation. That's why written oxidation. Okay, now anion approaches to anode and undergoing oxidation. If these molecules are two, if they are two, then what happens? Now how many electrons are released? 2 electrons. Now when 2 electrons are releases, RC double bond O radical. How many? 2. Now these 2 radicals undergo dissociation like this. Every 2. Now what happens? How many carbon dioxides are released here? 2 carbon dioxides. How many alkyl radicals are there? 2 alkyl radicals. Now these 2 alkyl radicals, here alkyl radical, these 2 get combined together and forms alkane. It is preparation of alkane. It will comes in that chapter. What we are preparing now? Alkanes we are preparing. At which terminal we are getting carbon dioxide? At which terminal we are getting carbon dioxide? Anode. At anode, what is the reaction takes place? Oxidation. Anodic reaction is nothing but oxidation. Loss of electron. After loss of electron, this carboxylate ion loses 1 electron and forms a radical. That radical dissociates and form carbon dioxide and alkane, dimerized alkane. Okay. Now, if you go cathodic reaction, so can I say cathodic reduction? Now, at cathode, which ions are going to come? Cathode. Cathode means which terminal? Negative. Negative terminal, which ions are going to come? Positive ion. See, this is positive ion. K plus. Now, K plus is approaching towards cathode. When K plus is approaching towards cathode, now whatever electrons released at anode, they are coming to cathode. Now see, these are the electrons coming from anode. Now this electrons is taken by potassium. Now potassium is taking electrons or not? Gain of electron is called reduction. Okay. Now K is get converted to K dot. It is taking electron from cathode. After taking this, now see, I am using water molecule. So every water molecule undergo dissociation, and that will give H dot and OH dot. OH dot combined with potassium and forms KaOH and forms H dot. Suppose if it is repeat 2 times, if it is repeat 2 times, how many radicals we will get? 2 radicals. And finally what is released here? Hydrogen gas. Now these 2 questions are common in case of Kolb's electrolysis. It will comes in alkane. Alkene, triple bond also this will come. In Kolb's electrolysis, carbon dioxide released at which terminal? This question is common. In Kolb's electrolysis, carbon dioxide is released at which terminal? Anode. Hydrogen gas is released at which terminal? Cathode. So they will give like this overall reaction. See, I am giving a methane attaches to C double bond O K. So what is this ion? Potassium salts of acetates. What is this? Potassium salts of acetate. When potassium salts of acetate on hydrolysis, electrolysis process it is. We are adding water and this too. And what we are doing now? And we are doing electrolysis. If I do electrolysis, what happens? Can I break this? See this. If this alkyl is a CS3, now CS3 become dimer. If CS3 dimer means what is the answer? CS3, ethane. Final answer is ethane. Clear? Then what are the gases which are removed here? Carbon dioxide, then hydrogen gas, and what is one more? After getting this, we are getting potassium hydroxide or not? Potassium hydroxide. Overall reaction, these 2 reactions I written it one place. And this reaction is called Kolb's electrolysis. Now in Kolb's electrolysis we are getting 2 gases, carbon dioxide, hydrogen gas. This question is important for your exam. where carbon dioxide, at which terminal carbon dioxide is released. If you know this mechanism, you can understand. Clear? Carbon dioxide released at anode. Don't confuse regarding terminals and ions. Always remember AA, now C, C. AA, CC. AA means anode, anion. Cathode, cation. Okay? Now this is an example of Kolb's electrolysis. Conversion of sodium or potassium salts of carboxylates to alkane with a suitable electrolysis process, and this is a dimerization reaction. We are taking one hydrocarbon. Suppose see, if I take ethyl here, I am taking CH3. If I take CH2, CH3, what is the answer? Here I am taking CH3. What is the name of this salt? Potassium acetate or potassium ethanoate. Potassium acetate I am using. When potassium acetate on electrolysis, what kind of alkane is prepared? Alkane chapter it is. Alkane, what we are preparing? Ethane. I want to prepare butane. What kind of salt is required? Potassium or sodium salts of? This is ethanoate only. Propanoate. Propionate, otherwise propanoate. 3 carbons are required. Now 2 carbons are there, we are removing this one. If 3 carbons are present, 1, 2, 3, 3 carbons, remove 1 carbon, left over 2 carbons undergo dimerization, you will get butane. So this I will explain in alkane chapter, but right now remember, key points are these two. Where oxidation takes place, where reduction takes place, where carbon dioxide is released, where hydrogen gas is released. This is key point in this reaction. You focus on these two. This question is compulsory if they want to ask alkane. Kolb's electrolysis, preparation of a alkane with a radical mechanism. So this is loss of electron. This molecule is losing electron. And what about here? This is plus means gain of electron. So this electron is coming from terminal. This electron is going from terminal. Difference is there. It is going from terminal. It is coming from terminal. It is coming from which terminal? Cathode. It is going through anode. Clear? So this is last one. Reaction with alkali medium. Acid base reaction we are using, and we are preparing one selective reaction. Tertiary butyl, and here I am using a hydroxy. Now to this hydroxy, what I am saying, I am adding a base. When base is added, alkali medium is added. Now this will take proton from phenol. When phenol loses proton and forms phenoxide ion. Phenoxide ion is a negative ion, right? It is a negative ion which carry -1. Means, is this anion having one extra electron or not? That extra electron have a tendency to react with this K3 FeCN6. Okay, like this I am writing. What is the oxidation state of this reagent? Potassium hexacyano iron 3. Okay, otherwise you can say potassium hexacyano iron. So what is the oxidation state of this iron? 3. 6 minus 3, you will get 3. Oxidation state is 3. Now in this one extra electron is here. This will donate one electron here, and this becomes a, how it is converted? Phenoxyl radical. This is called phenoxyl radical. And how this reagent is converted? This reagent is converted like this. Now here, when one electron is added here, when one electron is added, now this reagent initially, you can write like this or not? FeCN6, can I write -3? Is it -3 or not? If it is -3, now 3 potassiums get combined with this -3 and forms K3. Now if I add one electron here, -3 becomes -4 or not? Why? Because now this is giving one electron to this system. Now this becomes a -4. Then what is the oxidation state of iron? +2. +3 converted to +2. Now what is going on here? Is it oxidizing or reduction? This molecule is losing electron or gaining electron? Losing electron. So now it is a oxidizing agent. Right or not? It is doing oxidation on substrate. It is doing oxidation on substrate to lose one electron. So it is an oxidizing agent. Itself it is undergoing reduction. If they want to do oxidation on substrate, they should undergo reduction. Clear? So then what is this reagent? Oxidizing agent. It is initial position. Now this is final position after taking electron. So take one question. Free radicals are dash. Free radicals are dash. Stable neutral species. Stable neutral species. Paramagnetic charged species. Paramagnetic charged species. Diamagnetic neutral species. Diamagnetic neutral species. So option D, none. Free radicals are what? Is it stable neutral? Unstable neutral. If I say unstable neutral, this option is correct. Is it paramagnetic? Yes, it is paramagnetic. So this option is right. No, it is paramagnetic, neutral, but it is charged species. Be careful. Whatever points I given starting, you should learn clearly. Paramagnetic, charged. Yes, it is paramagnetic, but it is neutral. They are not charged. Now finally, is it diamagnetic? No. Answer is none. So that is about generations of structure and generations, both are over. Next, third one, stability. This already explained in GOC. Right now we will give one example. Stability of a free radical. Stability of free radicals. Is it free radicals are unstable or not? Free radicals are unstable paramagnetic species. They are get stabilized by electron releasing groups. So electron releasing groups increases stability of free radical. Free radical stability is completely explained by, it is explained by hyperconjugation. So complete free radical stability clearly explained by hyperconjugation only. Hyperconjugation is the best method to explain stability of a free radical. So if I take this molecule, can you say how many hyperconjugations are expected for this one? How many hyperconjugations? 9 hyperconjugations. Adjacent carbon hydrogen has been considered. Now if I take, this is CH3 and here one more hydrogen and this one. How many hyperconjugations? 6 hyperconjugations. And if I take a ethyl radical, CH3CH and here one more CH3 radical, how many? Both are same. This and this both are same, no need to confuse. Writing like this and this both are same. Okay? And if I write one of the hydrogen in place of this one, if I write like this, CH2 radical, how many hyperconjugations? 3 hyperconjugations. And if I write 3 hydrogens around carbon, how many hyperconjugations? No hyperconjugations. As number of hyperconjugation increases, stability increases. Can I say first one is more stable than second, third and fourth or not? That is the answer. Stability factors, tertiary is more stable than secondary, primary and super primary. So that is stability factor. Next, detection or trapping of a free radical. How to trap or how to identify a free radical? How can we confirm that in any chemical reaction intermediate is free radical? What are the methods to identify free radical as a intermediate involved in that one? First method. Okay. So when reaction is progressing, we need to add a small lead mirror. If you add a lead mirror, that lead mirror is going to collide with a electron, that is nothing but a free radical, and that lead mirror is completely disappears out. Okay. So first method to identifying is, what is that? Disappearance of lead mirror. A small lead mirrors are available in laboratory. That lead mirrors, if you add on chemical process, then what happens? See, free radicals will collide with that mirror and that mirror will undergo disappearance. So that is called disappearance of lead mirror is the first method. Okay. Next, see, rate of reaction increases by adding, okay, adding radical initiators. So what are the best radical initiators here? Hydrogen peroxide, otherwise you can write peracid. Suppose reaction is progressing one reaction is there which is progressing now. So A gives rise to B. Now it is completed within 5 minutes. Suppose if it is completed within 5 minutes, A gives rise to B. Now time is 5 minutes. Now suddenly what happens, I want to know whether it is proceeds with a radical mechanism or not. Suddenly what I added is a peroxide added. So then what happens, see, A is converted to B by adding a peroxide. It is a radical initiator. Now reaction completed within 1 minute. Now speed of reaction increase or not? Yes, when speed of reaction increases by adding a radical initiator, that is nothing but a free radical is one of the intermediate. If initiators are added, then rate of reaction increases. So we can confirm that radicals are intermediates in that one. So disappearance of lead mirror, it is directly a mechanical method, and this is only analysis method. Rate of reaction increases by adding a radical initiators. And one more, rate of reaction decreases by adding radical inhibitors. If I add a radical inhibitors, rate of reaction decreases. So best radical inhibitor is quinone. Carbonyl compounds, if you add, rate of reaction decreases. Suppose see, A to B, if I add, now what happens, the reaction completed within 5 minutes. Now same A to B, I observed by adding a radical inhibitor, this is called quinone, benzoquinone, like this. Then what happens, see, reaction rate decreases. Now it becomes 10 minutes. Speed of reaction increasing or decreasing? Decreases. Means it is one more confirmation that reaction rate is affected by radical inhibitor. So I am taking a vessel, this is one vessel. In that vessel what happens, see, reaction is going on. On that time what happens, I am adding a small mirror, this is a lead mirror. Now in this, suppose if radicals are generated, these radicals and this mirror will collide together and that mirror will disappear out. When mirror is disappears, it is a radical mechanism. By adding a initiator, radical inhibitor, if reaction speed increases, definitely intermediate is radical. And by adding a quinones, they are called inhibitors, means which will absorb the radical. Then what happens, reaction rate is decreases. So these are the methods to identify radical as an intermediate. So here suddenly sometimes what happens, see, there is a appearance and disappearance of color. When radicals are real intermediate, suddenly one color will come and they will disappear out. Okay, it may be a blue color, most commonly blue color, and we can also expect a pink color, depends on radical, it may be absorbed. One reaction is going on, simply we are watching like this, reaction is going on, we are continuously we are watching for 15 minutes. Suddenly what happens, pink color is appeared, slowly after completion of product that pink color will be disappears, which one of the evidence that may be a radical, we are guessing. On that time what we are adding a lead mirror, confirm, mirror is broken, may be a radical. Then we are adding inhibitors, reaction is getting slow, okay, it is a radical. Then finally we are adding a initiators, speed increases. These are the evidences. And very important one is, so remember, this is very important one, experimental method. Free radicals are isolated by, free radicals are trapped or isolated by ESR. This point is very important. Electron spin resonance. How a free radicals are single electrons or biradicals are get identified. Electron spin spectra. Electron spin resonance spectroscopy used to identify free radicals. This spectroscopy used to identify free radical is electron spin resonance. Electron spin resonance used to identify free radical. So these 5 methods you need to remember to trap or to identify a radical. Adding initiators, rate increases. Adding inhibitors, rate decreases. Adding lead mirror, mirror disappears. Okay? So appearance and disappearance is one of the easiest method to guess a radical. This is one of the easiest methods. So no need to do anything. Simply you need to focus. Why? Because it will come and disappear. That is one of the evidence that may be a radical. Then finally, the spectroscopy used to identify free radical is ESR. Remember, this is important point. Free radicals are isolated or identified by electron spin resonance spectra. Separate spectroscopy is there. Radical spectra, nothing but a electronic spectra. Inorganic spectra it is. Clear? So that is structure, generation, stability as well as detections of a free radical. Now chemical reactions. So one of the easiest chemical reaction in organic reactions are free radical reactions. Okay? This is chemical reactions of free radical. Free radical chemical reaction. So remember, free radicals involve in substitution and addition reactions. What are the two reactions you came to know in case of carbocation? Carbocation involved in which reactions? Addition, elimination. The first is rearrangement, addition and elimination. Carbanion. What about carbanion chemical reactions? First is condensation, substitution, elimination, rearrangement. Okay, so even you can also expect a condensation reactions for carbanion. Carbanion having more number of reaction. Now free radical only two. One is substitution, other is addition. Okay, so which molecules involve in substitution reactions? See, alkanes, and what is one more? Cycloalkane. Next here it is allyl carbon hydrogen, allyl carbon. Benzyl carbon involve in free radical substitution. One separate chapter is there. Alkane, cycloalkane. Okay. So alkanes involve in which reaction? Substitution reaction. Which substitution? Free radical substitution. Substitution nothing but what is our concept? Free radical only. If free radical involve in substitution, that is nothing but free radical substitution. Free radical involve in addition, nothing but free radical addition. Only two reactions, either substitution or addition. One more, dehalogenation is there, that is also substitution reaction. Dehalogenation is also nothing but substitution. Here substitution nothing but we are removing some atom in a molecule through radical mechanism. Okay? So listen, I am giving one example. This is a methane, right? Methane when reacts with chlorine photochemically. Now this reaction just now explained. When chlorine reacts with photochemically, what happens? Two chlorine radicals you will get. Now one is taken by hydrogen, methyl chloride, then followed by hydrochloric acid. Is it a methane? Methane gives rise to methyl chloride. Now which mechanism it is? Free radical substitution reaction. It is a free radical substitution reaction. Suppose if I take a secondary carbon and primary carbon. What is this? Secondary. And what is this? Primary. Now I want to make a chlorination under photochemical. What is the answer? Now out of primary, secondary, which carbon hydrogen is removed with a radical mechanism? Secondary or not? Can I write chlorine here? Chlorine. And what is removed here? HCl. Remember, in this I used chlorine. How many equivalents of chlorine I used? Okay, you don't know actually. So here one hydrogen replaced by one chlorine. If I use second equivalent, two hydrogens replaced by two chlorine. Then what is your answer? Dichloromethane, then chloroform, then carbon tetrachloride. So based on number of equivalents of chlorine, all hydrogens are possible to remove. If I remove first hydrogen with a chlorine, methyl chloride. If I remove second chlorine, hydrogen. Next if I remove three chlorine hydrogens, Next, if I remove all hydrogens around carbon, then what happens? CCl4. So these all products are possible in this reaction. It is completely depends upon termination. Where you are terminating, based on that only this product is depends. So that's why free radical substitution having 3 steps. Initiation, first is initiation. We are initiating chlorine or not? This reaction already explained. Photolysis, today's class, generation. When chlorine reacts with photochemically, what we are generating? 2 chlorine radical. This is initiated. Once if it is initiated, it will undergo propagation. That propagation may give this one, this one, this one, this one, etc. That depends upon your termination. So this I will explain completely with mechanism in alkane chapter. But right now it is not required. Only thing is, this will give a, alkanes will undergo free radical substitution reaction. That point you remember. Okay, many applications I will explain in case of alkane chapter. Okay, right now, alkanes reacts with chlorine, that will give methyl chloride, dichloromethane, chloroform, carbon tetrachloride. The formation of this product completely depends upon termination of the reaction. So you may expect all products here. Suppose if different carbon hydrogens competition comes, okay, always remember tertiary carbon hydrogen is more reactive than secondary carbon hydrogen, then followed by primary carbon hydrogen. It is a reactivity order for a free radical substitution reaction. Clear? So what are the chemical reactions you can expect for a free radical? Substitution, addition. So whenever if I use the word free radical, think about alkane. First alkane only. First chapter is alkane. Okay. So alkanes easily involve in free radical substitution. Don't say substitution. In substitution, 3 types of reactions are there. It will come in reaction mechanism. Free radical substitution, electrophilic substitution, nucleophilic substitution. So especially it will undergo free radical substitution. Alkanes are saturated hydrocarbons involved in free radical substitution. Addition reaction also possible, but they require a HBr or HCl with a peroxide initiator. So there is no required. Directly thermal or photochemical conditions are required to replace one of the hydrogen with a high electronegative element. Right? Now, see, just listen everyone. This is CS3. CH and this is CH2 I am writing. What is this carbon? Allyl carbon. Is this carbon is a saturated carbon? What is the meaning of saturated? Carbon which should not carry double bond. Which should not carry, it should not carry triple bond or double bond. That is a saturated carbon. Now it is a saturated carbon. Is it saturated carbon reacts with NBS in presence of CCl4? N-bromosuccinamide. This is called Hole-Ziegler reaction. One name reaction it is. N-bromosuccinamide in presence of carbon tetrachloride. It is a free radical substitution reaction. Why? Because what is this carbon? Saturated carbon. Saturated carbon undergo which reaction? Free radical substitution. This reactions only. Free radical substitution. Substitution nothing but free radical substitution in concept of free radical. We are in free radical. I written substitution. What is that? Free radical substitution. Now this is called N-bromosuccinamide. This is N-bromosuccinamide. Here bromine, C double bond O, C double bond O. This is called NBS. N-bromosuccinamide. When N-bromosuccinamide is given, this particular reagent undergo free radical substitution reaction, especially at which place? Saturated carbon. This is a saturated carbon. Remove one of the hydrogen with bromine. This is a free radical substitution, also known as Hole-Ziegler reaction. Okay, I will write that name, just you concentrate. See, this is benzene attaches to CS3. What is this? Is it a saturated carbon? Yes. Now it is involved in? See, when carbon having no double bond, if carbon having all single bonds, that carbon is said to be a saturated. Saturated means satisfied. Remember, satisfied. Satisfied persons involved in free radical substitution reaction. Okay. Now here see, if I use NBS in presence of CCl4, what is the answer? Can I remove one of the saturated hydrogen? See, here also hydrogen is there, here also hydrogen is available, but I am selectively replacing from saturated carbon. If I replace this CH2 Br, is it an electrophilic substitution? Yes. Is it electrophilic substitution? Free radical substitution. Don't forget our concept. Our concept is free radical. Now we are learning intermediate radical, free radical, don't forget. Okay, so now whatever reagents I am using, that will generate radical and that will replace hydrogen. See, hydrogen replaced by bromine through which mechanism? Free radical. That's what is called free radical substitution. Free radical is replaced. Hydrogen free radical replaced by bromine free radical. So removing allyl, what is this? Allyl. And what is this? Benzyl. Removing allyl or benzyl hydrogen with a bromine radical is known as, what is this? Hole-Ziegler reaction. It is one name reaction, these two. So removing allyl hydrogen, benzyl hydrogen with N-bromosuccinamide through radical mechanism, it is a free radical substitution. Okay, then that reaction is called Hole-Ziegler reaction. That you remember. It is one name reaction. Only allyl and benzyl it is applicable. NBSCCl4. Now these are the two reactions which are asked in CSR. So try to predict the answer. NBSCCl4. Here they given two equivalents. Sometimes they will give one equivalent or two equivalents like that. Use two times. What is the answer? These two are CSR questions. One more time we will explain in alkane chapter, and one more aromatic ring systems also it will come. Two areas it will come. If they want to target saturated sites, they will give NBS, N-bromosuccinamide in presence of a non-polar solvent. Here they may give any radical initiator or non-polar solvent they will give. If they give polar solvent, that may undergo electrophilic addition. Be careful with NBS, N-bromosuccinamide, Hole-Ziegler reaction. These two reactions asked in CSR exam. So where you will add bromine? So can I add bromine alpha to thiophene or not? So on this particular carbon, hydrogen is replaced by bromine, and in this one can I add one carbon or two carbons? See, here two possibilities are there. On one carbon you can replace two bromines, and one more, on two adjacent carbons can you replace two bromines, which is right? Two adjacent carbons you need to remove two bromines. Don't write two bromines on one carbon. Okay, so in mechanism I will explain, in NBS I will explain. It is a complete radical mechanism. Now, this is well known one for you. It will comes in alkene chapter. Olefin on treatment with HBr. Okay. Now, I am using a alkyl hydrogen peroxide or alkyl peroxide under photochemical. What is this? Very good. This is anti-Markovnikov rule. This is also called peroxide effect, Karash effect. Okay, peroxide Karash effect will be there, many names. Okay, Karash peroxide effect. Now, see, what is anti-Markovnikov rule? When negative part of the reagent is given, when unsymmetric olefin is given, then only you can apply anti-Markovnikov rule under peroxide. When peroxide is given, then only it is possible. Unsymmetric olefin reacts with unsymmetric reagent, negative part of the reagent added on olefinic carbon having more number of hydrogens. Which is negative part in this one? Bromine. So can I add bromine on terminal carbon? So if I add on terminal carbon, you will get bromine here. And what about inside? Inside should be hydrogen. So this is anti-Markovnikov rule. It is a free radical addition reaction. It is addition. See, we are adding hydrogen bromine on olefin. So we are adding, we are not removing, we are not substituting. Simply we are adding through radical mechanism. That's why it is an example of free radical addition. This is free radical addition reaction. Clear? So just listen. See, here I am using a benzyl halide. Benzene attaches to CH2. Now CH2 carry halogen. Now this halogen is reacting with a tributyl tin hydrate. This is called TBTH. Tributyl tin hydrate. In presence of, if I give ANBN, it is a radical initiator. Means reaction proceeds with a radical mechanism. Now, in last case what we learn, hydrogen replaced by a halogen. Right now halogen replaced by a hydrogen. So it is also free radical substitution. Now see, you may get CH3. TBTH, remember, TBTH is nothing but tributyl. This is, they will give like this, TBTH, tributyl tin hydrate, TBTH ABN, TBTH ABN, like that they will give. On that time, remember, the specialty of this reagent is they can remove halogen from variable places. The order of reactivity for this reagent is, first it will give priority for benzyl, then allyl, then tertiary carbon, secondary carbon, primary carbon, then followed by vinyl, even aryl also possible. This is the reactivity order for TBTH and ABN for removing halogens. So what is the reactivity of halogen? Which halogen is effectively removed here? Organoiodide is more reactive than organobromide, organochloride, then followed by organofluoride. It is a reactivity order. Remember this reagent. I will give these two combinations, TBTH and ABN. If this reagent is appeared in your exam, he will target halogens. Bottom one Mecombe reaction is there, 6-alloalkene, 6-alloalkane one reaction. So it can also convert acid halides to aldehydes and esters. Nitro to denitration reaction possible. Some selective reactions are there. So I will explain in tin OMC. There I will explain completely. But right now remember why we are concentrating right now. What is the reason? Why I included one reaction in this case? It is a free radical substitution. Is it a loss of halogen? Is it a loss of halogen from substrate or not? Loss of halogen is nothing but a, what is this? Dehalogenation. Is a dehalogenation reaction follows free radical substitution or not? Yes. It is a dehalogenation reaction which will follows substitution reaction. See. Now, can you give the answer? I am giving bromine, TBTH in AABN. What is the answer? TBTH in AABN. Can I remove that halogen? Can I write like this or not? Now it can remove irrespective of the orientation of halogen. Here I am giving bromine and benzene. Now TBTH in AABN. Can I remove this halogen or not? So if I remove this, can I put hydrogen? Yes. This all reactions are belongs to TBTH, radical mechanism. This is one exception reaction, just to remember. TBTH in AABN. Carbon-carbon triple bond. TBTH in AIBN. Just you listen, don't write, just you first you listen, later on you write. So many applications I will explain in TNOMC. Now one sample example and miscellaneous part I am explaining. Okay. So when tin is given, remember it is one of the excellent reagent to remove halogen, then lithium aluminum hydrate, then NaBH4. So which among the following is the best reagent to remove halogens from organic moiety means TBTH. If they want to ask any halogen related question to remove, best reagent is TBTH. And one exception reaction, this you remember. When halogens are given, double bond is given, exactly 6th position, if you start numbering from double bond, 1, 2, 3, 4, 5, 6. Is it 6th position or not? So I am start giving numbering from double bond, exactly at 6th position you will get a halogen. Okay? This is one of the most important miscellaneous example. So remove this halogen, remove this double bond, put a bond between 2 and 6. When you put a bond between 2 and 6, you will get a 5-membered and first carbon write down 1 hydrogen. That is the answer. This technique you remember. It is miscellaneous part, I will explain. It is kinetically controlled reaction, but still 5-membered ring formation is major in this one. We need to remove bond between carbon, halogen at 6th carbon. Always remember, when TBTH is given exactly 6th position, on 6th carbon, on any one of the direction, if you start numbering from one of the double bond, exactly at 6th position when halogen is present. It may be triple bond or double bond. See, this is called 6-haloalkene. 6-haloalkene. 1, 2, 3, 4, 5, 6. Break this, one of the triple bond. If you break triple bond, then what happens? You will get a double bond. You need to break only one bond. Out of 2 pi bonds, break only one. Now, if you count this, if I start numbering from one of the double bond, 1, 2, 3, 4, 5, 6. Is it 6-haloalkene? Now, on the time, put a bond between 2 and 6. Break this, put a new bond between 2 and 6. If I put a new bond between these two, see, C double bond O, put this double bond as it is. How many are there outside? 3. 1, 2, 3 are not. See this. 1, 2, 3. This is the answer. That's it. On first carbon, add 1 hydrogen. Second carbon, 6th carbon, put a new bond. Can I write a bond like this or not? That I written like this. And here always ring junction carries cis stereochemistry. This you remember. This will give a rank deciding question. When 6-haloalkene is given, give numbering from one of the double bond and you see in one of the direction exactly at 6th position halogen they will give. Okay? Remove that halogen, put a new bond between that 6th carbon and 2nd carbon and first carbon put 1 hydrogen. See, can I count from here? 1, 2, what is this? 3, 4, 5, 6, yes. Now, can you give the answer? First you remove the double bond. Remove the double bond and see this is O, oxygen, then followed by carbon, carbon. Can I write like this? Now what is present here? OET. That is the answer. And always remember, don't confuse. Here first carbon add one hydrogen. Here you write down cis stereochemistry. Here hydrogen and here hydrogen. Suppose if there is a methyl is present. If there is a methyl, this methyl hydrogen should be on cis. Here always junction stereochemistry cis to each other. This is a miscellaneous part. Actually I would like to explain in reagents, but right now I given one sample example. So try to remember. In many interconversions, this reaction will follows commonly. So that is free radical. This you remember, when TBTH is given in your examination, remember it is one of the excellent reagent for halogen. And whenever if this question is given, think about double bond. Exactly from double bond, if you give numbering, they may give more than one double bond, but only one of the double bond or approximately more than one double bonds are very closer to 6th position of halogen. So you need to count like this. One question is compulsory from this. It is one of the excellent reagent for removing halogen. What kind of reaction it is? Is it a free radical substitution or not? Yes. It is a free radical substitution. Halogen is replaced by hydrogen. So that is end of free radicals. So we learn free radical structure, then we also learn free radical generations, then we also learn free radical stability, detection, finally chemical reaction. So can you give what kind of chemical reactions will you expect for a free radical? Substitution and addition. Be careful, only two, substitution and addition. What kind of substitution? Free radical substitution only. Our concept is free radical, say blindly free radical substitution. Which molecules involved in free radical substitution? Saturated hydrocarbons. So can you give one example for saturated hydrocarbon? Alkane. Even cycloalkane also possible. Okay? Alkanes. What is the reactivity order? Tertiary, secondary, primary. Okay? So even unsaturated molecule also follow free radical addition by following anti-Markovnikov rule. Then finally we also learn some selective free radical substitution reactions by using TBTH. Only substitution addition reactions are there for free radical. So what is TBTH? Tributyl tenhydrate. What is the specialty of this reagent? This reagent can replace halogen with hydrogen, that is 100% free radical substitution. Exception in this case is exactly 6th position, one of the halogen they will give if it is started from double bond or triple bond. Okay? And try to remove that halogen, try to remove the double bond, put a new bond between 2nd carbon and 6th carbon, 1st carbon add one hydrogen. And when triple bond is given, don't convert them into single bond. Triple bond converted to double bond, add one hydrogen on 1st carbon, 2nd carbon, 6th carbon, create a 5-member ring. Finally, it is a kinetically controlled reaction. Many applications are there regarding TBTH, but all are free radical substitution. It can replace nitro, it can replace sulfur, It can replace acid halides to aldehydes even. Okay, and one more Barton-McCombie reaction is there, one name reaction, but these all things you will discuss especially in case of tin OMC. Okay, so that is end of tin OMC. Take a break. After break we will discuss what is carbene. Okay, take a break.